As you can see here, I've grouped together exercise for C, D and E because they're all obviously very much related. So we start off looking at trig ratios for angles greater than 90 degrees, and what we're going to see is that all angles bigger than 90 degrees can be connected back to an acute angle. So you'll see there's a connection between 30 degrees, the acute angle 30, then the obtuse angle 150, and the reflex angles of 210 and 330. So all four of those angles are connected. And all we have to do is find the pattern that connects them. And then you will see that the sine of 30 is connected to the sine of 150, 210 or 330. The same with cos and tan. All the trig ratios then of these angles, they're also connected. So there are a few things that we've got to look at, but mostly we're finding a pattern. So the pattern was identified by mathematicians that were extremely intuitive and came up with the concept of looking at a circle, radius r, and thinking about the points on the circle and their its relationship within a right angle triangle. So we're going to look at this circle and develop an understanding for sine, cos and tan of an angle in relation to this circle. Now, just let me put this in perspective. You have looked at sine, cos and tan in a very select group of triangles, right angle triangles, etc. You know that trigonometry doesn't only apply to right angle triangles, because you've heard of the sine rule and the cosine rule. So we know that sine, cos, and the trig can be related to angles other than angles in right angle triangles. So looking at this circle, radius r, allows us to do is to develop a more general understanding of the trig ratios and the angles of different sizes. So while you haven't used this circle previously, doesn't mean it wasn't there, and doesn't mean the mathematicians hadn't already developed the understanding. So what we're doing is we're just moving and expanding our understanding of trig, of angles that are not acute, and certainly there's a whole lot more to trigonometry and to angles that we won't look at either, but we're just expanding, like I said, into looking at angles of different sizes. So what was already established was that you can think of theta here in this circle and look at the sine of theta using, for example, opposite over hypotenuse, and so you would get that the sine of theta would be, and if I just call the point pxy, so it's y high, and we want that, the opposite side, over the radius. And the cos of theta would be x on r, and the tan of theta is y on x. Now that's going to lead us to a very interesting, another interesting trig property in a moment. And so this becomes our new definition for sine, cos and tan of theta. So we can then continue P around our circle and go into the second quadrant. Now, obviously, if I'm going to, if I'm in the second quadrant, then my X value becomes negative, doesn't it? Because I've moved along the X axis. And so we've got a negative X now. And my Y is still positive, so that sits up there at Y. I'm now going to talk about this angle called 180 minus theta. So it's an obtuse angle now. And according to my definition that it was established back here, the sine of theta should be the Y coordinate over the radius. Now, the mathematicians established that this works, and we actually choose a very convenient size of R, in that we'll make R 1. The mathematicians found that it'll work for any radius, but for our convenience, we're choosing a particular circle, setting our radius equal to 1, and knowing that it will work there and for any other circle, and it just makes it much easier for us to establish the pattern. So we're around, obviously, in the second quadrant. This is the first quadrant, second quadrant, and we go anti-clockwise in naming the quadrants. And we can see that by our new definition that sine theta is going to basically be the Y ordinate of point P. So we would have this time that it's still Y. It's a nice positive Y. We drop in R out, remember, because R is going to 1. And if that was, we were looking at comparing it to theta, if R was 1, then we've got exactly the same as the sine of theta, which was Y over R, which would be Y on 1. So we've got that the sine of 180 minus theta is actually exactly the same as sine theta. Here is our pattern. Moving then, let's do the cos. Cos of theta in the second quadrant, or cos of 180 minus theta, is the x ordinate, which we can see by our diagram is minus x. Now, cos of theta was x, basically x, although we had written x over r, we're substituting r equal to 1. So cos of 180 minus theta becomes minus the cos of theta, minus the cos of theta. Tan of 180 minus theta becomes y is positive over minus x, which is just minus tan of theta. So hopefully you can see we're developing a bit of a pattern. There is definitely connections between the acute angle and angles in the second quadrant. What about around in the third quadrant? So again, we're following the pattern that the sine of an angle is the y ordinate and the cos of the angle is the x ordinate, and the tan of the angle is y over x. So now P has moved around here, and obviously the x ordinate would be a negative again, and that now this time for P on your circle, it would have a y ordinate that's also negative. So sine of, now we're talking, the angle is 180 plus theta. And again, the way we name the angles in the quadrants is very important to observe. So remember back here, we just called the angle in the first quadrant theta. Here we were talking about 180 minus theta, and now in this quadrant we're going to talk about 180 plus theta. And so you can see that the sine of this angle, 180 plus theta, by our new definition, is minus y. Now, relating that back to in the first quadrant, minus y is the sine of theta. Cos is minus what x, which again is minus the cos of the acute angle, and tan is, well, it's minus y on minus x, and a negative on a negative make a positive. So, and y on x, I'll just scroll back, y on x was, there we are, y on x is tan theta. So, around in this quadrant, we've got that the tan of 180 plus theta, for example, 180 plus 30, which is your 210. So the tan of 210 is exactly the same as the tan of 30. There's your connection. Likewise, the cos of 210 is minus the cos of 30, and the sine of 210 is minus the sine of 30. Then in the fourth quadrant, we now are talking about, rather than doing 270 plus, we talk about in the fourth quadrant the angles being in terms of 360 minus theta, which you can see I've put there. The sine of 360 minus theta, again, it's the y ordinate, and p's moved around where x is a positive value, but y is still negative, so it's minus y, which is minus the sine of theta. So angles like 330 degrees, the sine of 330, which would be around here, is minus the sine of 30. Cos is the x value of the point. Now keep scrolling back, pause the video, keep scrolling back if you need to, just to check what I'm saying, which is straight out the cos of theta. So we would be saying that the cos of 330 is exactly the same as the cos of 30. We can also look at a graph and see that this is actually true. The cos of 30 and the cos of 330 are in exactly the same position in the graph. If I quickly just draw the cos. So we know that 30 degrees is in here somewhere. And then by the time we're almost, and we're back at 360 here, at 330 we're back there. So you can actually see even by your graph that the cos of 30 and the cos of 330 would be the same value. And this is just, I guess it's just another way of supporting the idea that we can see in the graph. But this is more, I guess this is more algebraic. The tan of 360 minus theta is again your minus y, your y value over your x, but at point P around in this quadrant, y is negative, x is positive, so that would be the minus the tan of theta. So in summary, no, I better stop the video there or I'll run out of time.